Again, thank you very much to the organisers for inviting me to this wonderful meeting. It's one of the most exciting places I've been in a very long time, and I'm having a great time here. We've heard quite a lot already about the question of how ultracold diatomic molecules collide with one another and whether they form complexes when they do, and my talk is another one on that topic, based on how the interpretation of some recent results from Simon Cornish's group on collisions of RbCs molecules. As I think everyone in this room knows, there are quite a number of groups around the world who can now make ultracold polar alkali dimers, typically 1 microkelvin or below, in optical traps, magnetoassociation followed by stirrup. It all started more than 10 years ago now, back in Gila with KRB. That was a fermion, and so KRB plus KRB collisions were protected. KRB was protected from another KRB molecule if it was in the same state. And so Julienne's group measured these very slow but temperature-dependent loss rates for KRB. But if they put half the molecules into a different hyperfine state, then S-wave collisions were allowed and the loss went a great deal faster. And everyone was thinking that that meant that bosonic molecules would decay very fast if they could, and it led to many groups trying to make bosonic molecules that couldn't decay by that kind of reaction. So that led to molecules like rubidium cesium, sodium potassium, sodium rubidium, and many more come along or just about to come along. But we fairly quickly found that all experiments using bosonic ground state molecules seemed to show fast collisional decay, even though we thought there wasn't a two-body pathway. And this talk is really about trying to understand what's going on in rubidium cesium plus rubidium cesium with some fairly detailed measurements and theory on that system. Now, when we're doing theory on simple collisions of relatively simple particles, and that means atom-atom, sort of 2 cesium atoms, or a simple atom plus molecule system, helium NH or something like that, what we're used to doing is close coupled channel calculations, essentially full quantum scattering calculations, putting in the full complexity of the atoms and molecules that are colliding. And that's perfectly feasible for these small systems, mostly the atom-diatom systems, and not particularly heavy atom-diatom systems at that. And I would just like to plug our MolSCAT program. We've got a new 2019 version of MolSCAT that's now available and on GitHub for anyone who wants to pick it up and play with it, with 200 pages worth of manual. However, such calculations become pretty heroic, even if you want to do something like lithium plus calcium hydride or lithium plus calcium fluoride, getting a bit heavier and with deep wells, or K plus KRB. They're not only heroically expensive, but they're also pathologically potential dependent. But by that, what I mean is that if you have an interaction potential and you change it by 1 part in 10 to the 3, which is far more accurate than it can be, the results get randomized. And so although you can learn some things about the general properties, you can't just take a potential and do calculations and have any realistic expectation that the numbers you get will be meaningful. When you come on to systems like RbCs plus RbCs, you can't do the full calculation at all. We just don't have the theoretical methods available to do the exact collision calculation. So we have to turn to approximate methods of one kind or another. And there are 2 classes of approximate methods that I'd like to say a little bit about in this talk and try and relate to one another. One is ideas of universal and non-universal short-range loss, and the other is models of sticky collisions going via complexes. I'm going to start by saying a little bit about both those ways of thinking about these complex collisions. So first of all, this business of universal and non-universal loss, which Idziaszek and Julienne really came up with to explain the original KRB plus KRB results. The basic idea is an idea from quantum defect theory, which is that an attractive r⁻⁶ potential has quite a sudden onset. And so a lot of the scattering bounces off that even though it's attractive, a lot of the scattering bounces off the fast onset of the attractive potential and never makes it to short range. Quantum defect theory allows you to work out how much of the scattering actually gets past the attractive potential and reaches short range. And then, for those that do reach short range, you think in terms of there being some probability for them just being sucked into products of some kind, and some probability that's 1 minus that for them to be reflected back out. And that tends to be expressed in terms of a parameter that was introduced and called y. It's not the probability itself, but it does have the property, the probability is actually this thing, but it does have the property that when y is 1, it means that everything is absorbed, and when y is 0, it means that everything is reflected, or at least everything that gets to short range is reflected. So you can think of y as a sort of a partial absorption and partial reflection for the collisions that get to short range. If you have 100% short range loss, that's called the universal limit, and it gives a particular loss rate that depends only on C6 and the coefficient of the dispersion attraction and the reduced mass. And when you plug through the numbers of that, you get a particular number that's about 10 to the minus 10 cc's per second for rubidium cesium colliding with itself. Key thing about the universal limit is that there is no reflected wave, everything gets sucked in. If there is no reflective wave, it doesn't matter a damn what the phase of the reflective wave is. And so there are no resonances, and the universal rate is the same for all systems where everything is sucked in at short range. An important point, though, is that the fact that you're in the universal loss limit does not mean that there's no elastic scattering at all, because a lot of the collisions at low energy do scatter off the attractive potential. Those ones never get to short range, those ones are reflected back. So you have a very well-defined and quite large cross-section for elastic scattering, even in the universal limit. Now, that's universal loss, but then you can have non-universal loss, and non-universal loss is just generalizing that to take account of the fact that less than 100% is absorbed at short range, some fraction is reflected. That fraction does need to have, there's a phase now for how that gets reflected at short range. So there's both the non-universal case, there's both this fraction of reflection, fraction of absorption, and a short-range phase shift. And that short-range phase shift maps onto a scattering length. It's not the scattering length, but if you know the long-range behavior, you can translate it into a scattering length, and vice versa. The other thing is that the original form of these universal models and the non-universal model was for S-wave scattering, but when you go to higher temperatures, you do need non-S-wave scattering, partial waves that are non-zero. Actually, you can do that within exactly the same framework. Bogau has told us the analytic solutions for an r⁻⁶ potential with and without centrifugal corrections. So it's a little bit more complicated, but you can fit it into exactly the same conceptual framework, and all these things about particles getting trapped behind centrifugal barriers and bouncing off centrifugal barriers just happen. So it's not too difficult to build in. if you've got a non-universal model, then what it gives you is a total loss rate coefficient. It does not give you product state distributions. It just tells you a rate coefficient for all the loss processes. It's a function of the collision energy, at least the way that we've formulated here, which is really quite similar to the way that Svetlana formulates it. There are only two parameters in these universal models. There's y and delta, the fraction of loss and the short-range phase, and as I say, delta maps to a scattering length. So it's useful to look at some contour plots of what happens. This shows you a rate constant for universal loss. Y equals 1 up here means universal. And this is a rate constant as a function of energy at the moment. And down here is the short-range phase, but in the universal limit, the loss rate is independent of the short-range phase. Then we can start varying y from universal. If it's 50% loss, you've got some fairly slow dependence on the short-range phase. We can go on 20% loss, 10% loss, 1% loss. So you can see that we're just increasing the amount of structure. This is actually an S-wave resonance. This is S-wave resonance scattering. These other things that crop up at different values of the phase, in other words, different values of the scattering length, are at other kinds of resonance. This is actually a D-wave resonance. This is a G-wave resonance. This is actually for identical bosons, so you don't have the odd partial waves in this one. So we can get these contour plots, and, well, I'll come back to using those contour plots in a moment. However, if we're dealing with these alkali dimers, how can these ideas of universal and non-universal loss apply anyway? They're all very well, but there aren't any two-body loss channels, so why are we talking about two-body loss? Where do the molecules go? Now, this is where we come into John Bone's ideas of statistical counting of numbers of channels related to the kind of thing that Thijs Carmen was telling us about yesterday. Before I talk about that, though, I do want to throw in a caveat about it. We tend to think classically, or half classically, I won't say semi-classically, of scattering that either bounces straight off or scattering that gets caught in a resonance and sticks around for a while and then bounces off. And that's all very well, and that's quite a good picture at higher energies, and it's well formulated and well understood. It goes back to Eisenbud and Wigner, a long time ago. And in quantum scattering, we can define this time delay, and you actually just get it from the energy dependence of the scattering phase shift. Felix Smith told us how to generalize that to a lifetime matrix for multi-channel scattering, but this is really for energies above the ultracold regime. And there, it's true that non-resonant collisions are usually short-lived, and the time delay peaks at resonance. So you get something like this green picture, which shows how the time delay, this shows the time delay peaking at a resonance with a much lower background than at resonance. Unfortunately, this doesn't really work once you get into the ultracold regime. In the ultracold regime, it turns out that at low enough energy, the time delay is just proportional to the scattering length, and that can be both positive and negative. And so most of your ideas of resonant scattering being long-lived don't work properly. That's not something I want to go into in this talk, but I just want to flag up that the whole issue is more complicated than most people seem to think it is. However, let's go back to the sticky collisions idea for cold molecules. It goes back to these papers by Myler et al. In John Bone's group, and they came up with a statistical model, and they pointed out that both 3-atom and 4-atom collision complexes have pretty deep wells, and that if you evaluate the density of states at the top of those wells, you get very large numbers. This is exactly what Thijs was talking about yesterday. Thijs sort of corrected the original numbers that John Bone came up with, But still, the principle is that you get pretty large numbers. And if a long-lived complex is formed, it's possible that it gets destroyed before it falls apart again to give you your original molecules back. John Bone's original idea was that it would be destroyed by collision with a third body. Tice talked about that being a laser-driven process, and those are true. Those, we need to understand what's happening. But either way, you get, if the formation of the complex is the rate-limiting step, you get second-order kinetics for the decay of the molecules, not third order. So even if it is a three-body process involving two coming together and a third one coming along, provided the lifetime is long before a third body comes along, you still get two-body kinetics. And in Tice's model of it being a laser, you certainly get two-body kinetics. So the original estimates gave, a 10 to the 2 to 10 to the 4 levels per Kelvin for triatomic ones, and more like 10 to the 9 levels per Kelvin for tetraatomic ones. Those, everyone recognized that those were very drastic dynamical approximations, and as Tice pointed out yesterday, those are estimates, possibly overestimates by several orders of magnitude. But they made another key approximation, which is that they assume that all the levels that are there are statistically sampled. And they introduce that in a particular way. They have a mean level width, gamma, which is basically equal to the level spacing with this additional factor of the number of open channels in front. And that's an approximation that you can see that comes from various possible places. You can think of it as coming from our RKM theory. You can think of it as coming from random matrix theory. They estimated a lifetime of 45 milliseconds, as Tice said yesterday, probably really much shorter than that. But they had another key result, and this key result's in their second paper. And the key result is that provided the complexes last a long time compared to whatever destroys them, it doesn't matter what the density of states is. Under those circumstances, you get the same loss rate as the universal limit, which comes from a completely different derivation. At least in the ultracold limit, you get the same result. So even if complex formation is what's going on, it's really useful to use these universal and non-universal ways of thinking about it, and then maybe interpret the results of that in terms of these ideas of mean widths and mean lifetimes of the complex. So that's sort of the theory background. What Simon's group have done are that they've taken clouds of RbCs and measured the lifetimes, measured the time-dependent loss profiles for them. And they've done this for the ground state and for some hyperfine excited states and for some rotational excited states, but I'm only going to be talking about the ones for the absolute ground state today. And this is the first point, which is here's the time profile of the loss, and here are fits to it to this formula, so, which is for first order, second order, or third order kinetics. I don't want to say two body, three body, because order and body are not the same thing. But this loss profile very nicely fits the second order kinetics, and it really doesn't at all fit either first order or third order kinetics. And they verified that by varying the initial molecule number, and okay, there are big error bars on here, but again, first order and third order are both a long way away from what they observe. So this is pretty convincingly kinetically second order loss. So that really, so far, that does support a mechanism that goes via complex formation. It's quite hard to come up with anything that gives you a rate determining step that's second order except complex formation. However, when you look at the actual numbers, it does not disappear at anything like the universal rate. They measure quite well-defined number for the second-order loss coefficient. Here it is. If you evaluate the second-order, the universal rate at 0 temperature, then you get something that's a factor of 4 different, roughly. But even if you put in the higher order, the higher partial waves, which are important, and the proper dependence of the S wave one, you still get something that's a factor of more than 2 different. So this is going at half the rate that it would if it was universal loss. So what do we learn from that? What do we learn from the fact that this is not universal loss? Well, if we take those plots that I was showing you earlier and represent them a bit differently, what this shows is that this is the thermal average at a specific temperature, one of the temperatures of the experiment, 1.5 microkelvin. But it shows the loss at that temperature as a function of this loss parameter and the short-range phase. And on that diagram, the experimental number and its error bars limit you quite a lot to this. So the best fit is the solid black line, and the 1 sigma bounds on it are the curved black line. I wouldn't care to express that as numbers, but that's those are the ranges parameters that are emitted by the data. There's a tiny little thing here, but we won't worry too much about that. That's due to D-wave shape resonances, and it was conceivable at this stage, but was ruled out by the next stage. So this is telling us that it's clearly non-universal. Y is less than 0.4 everywhere here, but it's not at this point telling us anything about the short-range phase. So let's look at this in a little bit more detail. If we've got universal loss, the loss rate does depend on the short-range phase. What we can do is we can work out what the temperature dependence ought to be at each point along this fit. So for each value of delta, we can pick the values of y that are allowed for that delta, and we can work out what the temperature dependence would be for that. So that just says that. And that gives us this. So the various dashed lines and this solid blue line are all possible temperature dependencies, all of which go through the experimental point at 1.5 Kelvin, but are dramatically different, have dramatically different temperature dependencies. So you see this one here, actually, this is resonant, near resonant S-wave scattering. This one actually goes off. So the universal limit is here. We're not comparing with the universal limit. We're comparing with these 4 different colored lines. The solid blue is the best fit to this set of experimental points. And it has specific values of both this loss parameter and the phase. So the first point is that if you have the temperature dependence, that is very sensitive to the phase. So we can now refit those experimental data, putting in the higher temperature as well, higher and lower temperatures as well, and we end up with a much nicer, a much smaller area of y and delta that can fit the experiments. So we end up with y as about 25% plus or minus 0.03, and delta, which we've expressed as a multiple of pi, with a certain number. But if we express that as something more familiar, which is a scattering length, it tells us, gives us the first indication we've got of what the scattering length for one of these molecule-molecule collisions might be. Now, this is some kind of hokey, vague average scattering length, but nevertheless, it's telling us something about how close to resonant S-wave scattering we are for these collisions. So, what does this tell us, all in all, about the mechanism? First of all, the simple fact that its second-order loss really quite strongly supports complex formation. Secondly, the original model of Myler et al. Doesn't work quantitatively. It predicts, the model would predict a rate that is the same as universal loss, and experimentally we get about half that, and that half is highly significant. One thing to note, I mentioned this when I was talking about the model to begin with, it doesn't actually matter what the number for the density of states is. This experiment is not giving us an effective density of states and telling us that the effective density of states is smaller than the Myler model. In other words, this result is not explained by what Thijs was talking about yesterday. But the rate does depend on this RrKm assumption, this assumption that the complex is behaving in some sense statistically, that formation of it's behaving statistically. And the fact that we're not getting a universal rate really tells us, we think, that RrKm statistical model of what the levels look like is breaking down. So really, only a fraction of the complexes that are formed are destroyed, and that is possible. But if all the complexes that are formed are destroyed, this tells us that the process of formation of the complexes is not statistical. And you can express that in various different ways. You could say that means that the mean width, for which there's a very well-defined expression in our RrKm theory, is smaller than our RrKm gives us. You could say that it means that the level pattern is more structured than random matrix theory. I think that's something that, yeah, I've kind of always thought it ought to be. Because real Hamiltonians have structure. Real Hamiltonians are not random matrices, and so it seems to me to be an unexceptionable result that the real level pattern is more structured than random matrix theory. Or you could view it as saying that the closed channels, the channels that describe the complex, are not statistically coupled to the incoming channel. You can pick whichever of these languages you prefer as your way of thinking about it. Another way of thinking this that I quite like is that it could be that there's a geometric restriction on complex formation. In other words, that complex formation can occur when molecules collide at some subset of relative geometries, but not at other sets of relative geometries. I think that would have this effect of making the mean width smaller than predicted by our RrKm theory. But one way or another, I do think that this is telling us that we have a lot more that we need to understand about these processes, and that the non-universality of this rate actually has important, well, not important consequences, but important interpretations in our understanding of this complex formation process. So that's pretty much the story, except to thank the people who did the work. First of all, I want to make it quite clear, all the experimental work here was done in the group of Simon Cornish. Simon is here. It was led by Phil Gregory in Simon's group. The guy who did most of the theory work that I've actually presented is Matthew Fry here, who's a great postdoc. But Thijs Carman was in my group for a while, a little bit before this specific project started, and we spent a lot of time talking about this, so I have a lot to thank Thijs for in my general thinking about these projects. It's on archive. For some reason my abstract isn't linked in the conference program, but I can easily send a copy of the abstract to anyone who wants it. So thank you very much.
Thank you very much, Jeremy. Very interesting and quick question. Yeah, Concrete?
So I guess it's very interesting. So the rubidium cesium, I guess, case is quite different from sodium potassium in my opinion, because sodium potassium is a fermion, and that this three body and like a sticky, and then the third body that comes, that Thijs has suggested that time scale would be 1 second. That was based on, I guess there's no Fermi suppression there, but the density was quite low. So would a third body that comes could still the time scale for this will be very different. Right?
Yeah, absolutely. But most of the stuff to do with the difference between bosons and fermions is in the quantum defect theory part of it, in the long range part, and that handles the bouncing off the long range potential. I think as far as the actual density of states is concerned of the complex, it doesn't make very much difference whether it makes some difference whether they're indistinguishable or not.
In terms of the third particle that comes, the time scale for that, is that very different?
Well, the third particle is a molecule colliding with a complex, so you don't have any fermion suppression at that stage.
I guess then there will be just density dependent.
Yeah, I think so.
Which
Yeah.
I think in this case will be an order of magnitude faster, just from the density difference compared to the number you use. So.
I'm not quite sure. What do you mean by this case? Do you just mean RbCs as against other systems? Okay, but the potassium 39, sorry, potassium 40, I mean.
Right. So could that still be? I mean, I guess it may just be an order of magnitude, which will knock it down to 100 milliseconds and still do slow.
It's tight.
We have estimates of this, and so we yesterday also gave the lifetimes that you would expect if there's only that loss, and this is sort of minutes for rubidium cesium. So I don't know if that.
I think what we're talking about is essentially independent of what it is that destroys the complex. You know, I mean, the modelling here applies whether a third body comes along and destroys it, or if a laser comes along and destroys it. Either way, what we're really attributing this non-universality to is the process of the formation of the complexes, not the process of the complexes falling apart. So we're seeing it as an entrance channel effect.
Yeah, one more question up there. Yeah, please.
So, can you comment on the effect of non-adiabatic interactions on these lifetimes?
So the various calculations of the lifetime so far, I mean, both John Bones and Tice's corrected version of it have no concept of diabatic or non-adiabatic in them whatsoever. They just assume that the entire energetically accessible phase space is sampled and that it's ergodic.
Because here, this is the way normally implemented in any QDT. You do this by a vibrational or rotational frame transformation in the asymptotic region.
Right. So what we've got a single incoming channel here.
Okay.
And that single incoming channel, so it's two RbCs molecules in their ground, rotational, and everything else state, and they have a large C6 attractive C6 because of rotational dipole interactions, but it's a single channel model for the incoming part. So in that sense, there's no diabatic versus adiabatic.
Could you just briefly explain? You had curves which go above the universal limit. What do you think about this?
Okay, so in the absence of resonances, you can't have anything faster. So the universal limit is everything comes in, and some molecules come in, and everything that gets to short range is destroyed. If you have resonant S-wave scattering, then you have an amplification between the long-range wave function and the short-range wave function. And so, in a sense, the QDT is giving you an enhancement, and so you can have a greater probability greater probability of loss than you would in the absence of that. So it's a resonance, and resonances can give you peaks above the average, and in a sense, the universal is just the average, without the possibility of resonant enhancement.
You mentioned that it is possible that your formation of complex, not totally statistical. Do you mean in sense of statistical approach, which actually separates two regions totally when you look at collision starting from like a mixture from reactant to the complex, and then totally independently looking after?
I think the separation between the short range and the long range is a different thing from the question of whether it's statistical or not. The question of whether it's statistical or not is really a question of the structure of the complexes at short range, or rather the Hamiltonian matrix for the complexes at short range. So if that matrix is completely unstructured in a statistical sense, in other words, it's given by random matrix theory and the Gaussian orthogonal ensemble, if we want to be specific, then you get the RrKm result. If that Hamiltonian is not random, if the eigenfunctions of it don't sample the whole of space, which is pretty much the same thing, then you will get something. Then you can't use RrKm. So it's non-statistical in the sense that the complexes don't sample the space ergodically.
One more quick question.
Yeah, I think I want to make a comment that is experiment can really contribute about this picture if you actually measure the resonance width, for example. Experiment like for example this kind of picture about the talk about lifetime of the complex. Well, I know that in atom molecule is certainly not quite right. I mean, atom molecule, so you have the rotational Fishbach resonances, and those resonances, the width is actually dependent on the anisotropy of the interaction.
I mean, I fully agree that what you'd like to be able to do is resolve these resonances and measure them, but the experiments that we have at the moment are so far away from being able to do that we kind of have to make the progress with the experiments that we've got. I do.
Actually, it's an experiment that will really tell us for sure, but theoretically, I know in the atom molecule, the lifetime is determined by the anisotropy. I mean, well, for the most part.
Yes, but that's in a perturbative regime, and a big so that's in a regime where you kind of have a bound state wave function that you have a zeroth order picture of, and you have a scattering wave function that you have a zeroth order picture of, and you can calculate a matrix element of a well-defined thing like the anisotropy between the two of them. There's a big question whether these systems are of that nature where you have a zeroth order picture and you can calculate matrix elements, or if they're in a different regime where the couplings are so strong that everything has virtually become statistical. And those are different ways of looking at it. And if they are statistical, you simply can't think about it in this nice small molecule picture that we're all familiar with and love. I think Theis's results suggesting that the density of states are not quite as high as we had feared are actually making us hope considerably more that we will be able to do these kind of precise measurements. If the densities were as high as John Bone had said, it's going to be a long time before we can measure those. If the densities are much, much lower, maybe we will. We'd like to.
Okay, I think we have to move on. Thank you very much.
Thank you.